to talk about nothing. But when we talk about nothing, we have to be a little more precise, I have learned. Because people get upset by the idea of nothing. I would argue, and I still argue, in spite of many people who argue the contrary, that nothing is a physical quantity, not a philosophical quantity. Because something is a physical quantity. And so in order to understand nothing, we have to understand something. And the point is, science has changed our understanding of both. So the first answer to the question, why is there something rather than nothing? And by the way, that question is really, how is there something rather than nothing? Because the why question is unimportant. Why is there something, I use the why question because I'm stuck in the jargon of the time. Why is there something rather than nothing? The simple answer is, because nothing is unstable. The surprising thing would not be that there's something, but rather that there's nothing. But then, of course, it wouldn't be around to ask the question. Because it turns out, because of those particles popping in and out of empty space, once I add gravity into the mix, so I can create particle-antiparticle pairs that have zero total energy because of their gravitational attraction, they can persist forever. So if I have no particles to begin with and just empty space, the nothing of the Bible, if you wish, an eternal empty void, and I wait long enough, quantum mechanics guarantees me particles will be produced. They'll spout out of nothing due to the laws of quantum mechanics. So it's very simple. Nothing is unstable. You wouldn't expect to see nothing. You'd be very surprised if there were nothing. Okay. Now that, however, does not satisfy many people. Well, because it gets rid of God, for the first part. But also because, well, it doesn't really look like nothing. After all, even though there's nothing there, and there is nothing there in empty space with waste stuff, those particles aren't real. There's nothing there. You could, from now to eternity, try and see what's in there, and you'd see nothing. Okay? So it really is nothing in that sense. But nevertheless, space is there. So this is, but before I get there, let me just summarize. I forgot I wrote it down. So, if you have empty space, you can create real particles with zero total energy, and you can do it without any you don't need God. You don't need some outside intervener. The universe can do it all by itself. Okay? The nothingness of the universe. But, as I point out, that doesn't seem like it's nothing, because although I don't have particles and I don't have radiation, I've got space. Where the hell did the space come from? You might ask, especially if you don't like this answer. And the answer to the second question is very simply, gravity, Einstein's general relativity, is a theory of space and time. If I make general relativity a quantum theory, and we can't yet, we don't have a theory for quantum gravity, but we have some ideas, good ones and bad ones. But whatever theory of quantum gravity ultimately exists will make space and time quantum variables. And quantum variables fluctuate. That's what causes virtual particles to pop in and out of existence in empty space. That, in fact, as I'll describe, is what we think caused those lumps that eventually created us and everything we can see, quantum mechanics. We are here as a direct result of quantum mechanics. But if I make space and time quantum mechanical at the very beginning of time, then quantum mechanics will allow space to be created, universes to be created where none existed before. Space and time themselves can fluctuate into existence and fluctuate out of existence. I can create universes and spaces where there was literally no space or time before. Most of them will disappear in an instant, just like our virtual particles. But if I create a universe that has zero total energy, that universe can persist forever. Now, it all sounds great, because I just told you in a flat universe, every object has zero gravitational energy. So it would really be nice if that was the end of the story. But it's not. I gotta be honest. It turns out we can't calculate the total energy of a flat universe. The gravitational energy of every object in a flat universe is zero. But Einstein told us E equals mc squared. So objects have rest mass, and they have energy. Okay? And it turns out the only universe for which I can calculate the total energy and find out it's precisely zero was a closed universe. A finite closed universe. That's not the universe in which we live. Well, that's true. But most closed universes will collapse. Remember I told you they'd collapse? In an instant, in a microsecond. The only kind of closed universe that can survive long enough for us to be around to ask the question is one in which, for a little while, there's an energy in empty space. That energy in empty space is gravitationally repulsive, and it'll puff up that closed universe to be a very large scale. And that is exactly what particle physics predicts should have happened in the early period of our universe. It's a phenomenon called inflation. Good thing to talk about at the London School of Economics. But this is inflation we understand. Particle physics says at early times, I don't know if I have it. I wonder if I have a picture. Yeah. Okay, I'm going to talk about this. I'm going to talk about beer. I grew up in Canada, so there's a lot of beer. If any of you, the little children shouldn't listen to this. If any of you have ever had a party and you bought some beer and you forgot to put it in the fridge, what do? Well, you do what I do, you put it in the freezer, right? And then you forget about it. Then what happens? Well, you open it up and suddenly crash! The bottom breaks and the beer suddenly freezes. Why? Because under high pressure the beer was liquid. But the minute I opened it up, the beer changed state. It froze. And when it was liquid, it was called a metastable state. And when I opened the top, it could release energy and break open the beer box. Our picture of the early universe is precisely that. That as the universe was cooling down, it got stuck in a metastable phase, a state, where empty space had energy stuck in it, large amounts of energy, causing the universe to expand by a huge amount, a factor of 10 to the 90th in volume, in a time period of a millionth of a billionth of a billionth of a billionth of a second. It sounds impossible. It sounds crazy. But it's predicted by the theory. Moreover, it turns out during that period, we can calculate what will happen. And it turns out quantum mechanics will produce fluctuations which get puffed up and made very big and get frozen at early times and get turned into density fluctuations that might one day collapse and form galaxies. And if we ask what would that distribution of fluctuations look like, it would look just like the picture I showed you in the cosmic microwave background. That gives us great confidence, in fact, that this picture is probably true, and you are here literally because you're resulting from quantum fluctuations. But for the point of what I want to talk about, go back to what I said before, and by the way, that phenomena is precisely the kind of phenomena that now has greater validity because we may have discovered the Higgs particle at the Large Hadron Collider. The Higgs particle also tells us that there's some uniform background field throughout the universe, called the Higgs field. But this idea of inflation requires a different field that gets stuck in a uniform phase in the early universe, and it was very slimy, that prediction, because we didn't know of any fundamental scalar fields that should exist. But now we seem to know of at least one. So this picture has gained currency. The picture of inflation is now much more believable without beer. So if there's a period of inflation, it'll puff the universe up, but just like if I blow a balloon up, and make it very big, say the circumference of the Earth, it looks flat. The Earth looks flat in Kansas. And so our universe, the only kind of universe that could survive, a closed universe that could have been created by quantum gravity, that would survive long enough to survive to the present time, is a universe that looks flat. Precisely like the one we live in. So, no space, no matter, no radiation, no space. It can all come from a quantum fluctuation, and it will look precisely like the universe we live in. Some people say, however, okay, well that's okay, you got no space, no matter, no radiation, but what about the laws? What about the laws? Who created the laws? And the interesting thing, although it's depressing, is even the laws of physics themselves may be accidental. And the reason for that is this weird energy of empty space that we don't understand. People have said it's so inexplicable that maybe we can understand it as following. Turns out if it was much bigger than it is, no galaxies would form. So let's say there are not one universe, but many different universes. And the energy of empty space can vary in each one, and then only in those in which it's not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure. It sounds ridiculous. It sounds like a tautology, it sounds religious almost. It's neither. It's kind of cosmic natural selection. You know, Darwin told us that the diversity of life on Earth wasn't designed. Bees can see the color of flowers, not because they were designed to do it, but if they couldn't, they wouldn't find the nectar that would allow them to reproduce. Well, we would not expect to find ourselves in a universe in which we couldn't live. We'd be quite surprised. So if this is true, it's not that surprising. It just says there are many universes. We find ourselves living in a universe in which there are galaxies, and galaxies can allow stars and planets, etc. It's a depressing thought because it means at some fundamental level, this fundamental quantity, the energy of empty space, is an accident. But particle physicists are way ahead of cosmologists. Because, you know, cosmologists don't understand one number, the energy of empty space, but particle physicists haven't understood many more numbers for much longer. We don't understand why gravity is the weakest force in nature. We don't understand why the proton is 2,000 times heavier than the electron. We don't understand why there are 3 generations of elementary particles. And so particle physicists have jumped on this and said, maybe we don't have to understand anything. Maybe it's all an accident. Maybe if any of these things were different, life wouldn't have arisen. And in every universe, these numbers are different. And then we don't need a theory of everything. We just need a theory of anything. And we have a candidate theory. It's called string theory. So I want to give you one slide on string theory. Those who've never heard of it. One guy says the other, I just had an awesome idea. Suppose that all matter and energy is made of tiny vibrating strings. Second person says, okay, what would that imply? First person says, I don't know. That's the history of string theory over the last 40 years.